Yes, good. So my name is Yerzhan Zhamashev, and I'm here with my business partner.
Eero Keltikangas.
And we are here to talk about how we can bring cloud computing capabilities to the network edge with WebAssembly, with current standards. And here is a short outline on what we are going to talk about. So main theme is we are going to mention the context about industrial IoT architecture, what kind of challenges there exist, just a reminder on that, and then how WebAssembly and standards around WebAssembly would help in solving those problems. Then mention about available cloud and hardware interfaces when working with WebAssembly, and then slowly transition to how the deployment and orchestration currently works with WebAssembly with a short custom setup demo running WebAssembly on this little edge device. So let's get started with the industrial IoT architecture. So you've probably seen this layered architecture overview of edge computing several times, but the basic thing is, especially in industrial IoT environments, you would like to bring computation closer to the machines to achieve lower latency, if necessary data locality, and deploy applications that are more resilient to intermittent connectivity, so that if the centralized cloud connectivity is lost, your applications on the factory floor would continue running without interruption from the network. So that's the main challenge. And interesting thing to mention here, on the right side I have consumer apps, but consumer apps mostly are web applications these days, and it's an open standard where WebAssembly is originated from. However, now it's going to the other direction as well, from the centralized cloud to the devices, treating kind of devices like browser environments. And the challenge is to build open standards around how you would run WebAssembly on edge devices, just like in browsers. So the focus is on the problems that we need to run the logic on the device. So as mentioned, or in the edge environment, especially industrial IoT, you have diverse hardware. Those hardware are mostly resource constrained. There are plethora of various interfaces that you need to interconnect with. And you would like to also include some sort of cloud integration, maybe for remote updates, to make the orchestration of your workloads more easier. And I'm not sure how many of you are familiar with WebAssembly, so that I know if I need to have an introduction for it. Can you raise your hands if you heard about WebAssembly and know what it is? Okay, so the short explanation of it is bytecode format that can be compiled on the machine, just-in-time compilation, ahead-of-time compilation, and then it would run on your device with native or close to native speed, because it comes with its own limitations on how it is designed, of course, because it is designed for sandboxability in the browser with its linear memory, and the standards with interfacing with it is based on WebAssembly standards. So it kind of resembles JVM, also bytecode format. However, in its current form it is way more simpler. However, it's being developed further with more proposals coming in, which I will mention later. And you can sort of imagine it as a reinvention of compile once, run anywhere. It's not like a Java virtual machine nowadays, and the standards around it are developing in a completely different direction. So because it's a low-level bytecode, it can run on diverse hardware, just like JVM, but because it is also simple, with current tooling, it is not so difficult to run it on resource-constrained devices. So I will skip that part for this presentation to save up some time, and the thing to focus on is interoperability. How would you add your custom interfaces to communicate with your hardware capabilities, and how to integrate that with the cloud while keeping that interoperability in place. So to solve the solution, we need to go with a standards-based solution. We have several standards being developed around WebAssembly, namely WebAssembly system interface, the new component model, and WebAssembly interface type. That's interface definition language for WebAssembly components. And another latest development is WebAssembly interface types over remote procedure calls, which is enabling some new use cases on how to run WebAssembly workloads in the cloud. So here is a simple diagram on how you compose different interfaces together. It can be a component composed together with another interface adapter, for example. You may have generic interfaces for publish, subscribe, but then have an adapter that integrates tightly with MQTT, also compiled to WebAssembly, and then have your MQTT client running in your host environment, which communicates with some MQTT broker. Similar setup for HTTP server client implementation. And another thing to mention is remote procedure calls for WebAssembly interface types, if that remote procedure call endpoint is implemented on your provider. So, like crazy idea, you can have GPIO going through a remote procedure call if your Wasm component is running somewhere where GPIO is not available. So that's quite possible. So I think that's a cool part to explore. So WebAssembly system interface is a set of standards and API specifications for software compiled for WebAssembly components. Although you can define your own interface with WebAssembly's interface type, these are interfaces that are standardized and included built-in most of the runtimes. I highlighted the ones that are fully standardized and included in most of the runtimes, but there are also standards that are not yet in all of the runtimes for WebAssembly in the server, and some of the ones are in early proposal stages. For example, GPIO, USB. They have some proof of concept implementations, however, it's not available in general purpose runtimes. And some proposals are just being discussed and developed in early development. And the beautiful part of defining those interfaces is that you can put an abstraction at any layer and deliver based on your needs of the platform. So you can put an abstraction based on if you want to deliver the native speed of your platform, if you want to integrate with legacy code base, so for that is exposing some interface that you need to still work with, or if you need to compose with other components that are compiled now to work with certain interfaces. So in this case, for example, there is a WebAssembly system interface standardized for HTTP, but also for sockets. So you can have the whole HTTP server and client compiled to WebAssembly component, but you can skip that part and make your runtime responsible for handling HTTP requests instead. So this setup is pretty flexible. So this is an example of Wasm interface types that I was mentioning, which is a specification language for the component model, describing the contractual boundaries between your components. And there is an example for GPIO access taken from the proposal in WASI GPIO. You can see that it kind of conceptually also, if you've done C programming, kind of reminds you of header files. However, it goes a bit more beyond that, where you are defining your interfaces, custom types. You can import interfaces and types from other packages. For example, here it is importing from WebAssembly system interface for input-output, or from locally defined types in your directory for the interface. And here there are simple functions, namely the custom resource for input-output pin, where you can, just like any input-output pin, put the values for high or low and control some external device with it. So GPIO USB I2C standards are being developed with researchers in the field, and I found, at least I connected with some of the people at Ghent University, and they released a paper recently on cyber-physical WebAssembly, exploring proof-of-concept implementations for WebAssembly components to interface with device GPIO, USB, and I2C. This paper, I think, is mainly focusing on I2C and USB interfaces, and describing how to enable capability-based security. So by default, for example, you would get permission errors for or not implemented errors for accessing certain resources. But if your runtime allows your component to execute, to communicate with the interface, you would get fine-grained control for capabilities provided by your hardware or platform. So in the hardware interfaces with GPIO, you can configure modes, read-write pin states, toggle output. With USB as well, you can list open devices. It is also similar to the web standard web serial and web USB available in Chrome. I've seen some companies that use that web standard to enable some browser-based games with their custom hardware, and this one kind of resembles that as well. So you have available devices, and if your runtime allows it, you can claim certain USB device and then perform control over it. And then similarly, I2C, you can read-write I2C transactions with that interface. And even though we've defined here low-level interfaces for hardware access, it is also possible to define cloud core interfaces to deploy your application on the cloud, to develop more or less distributed systems. And from the standards, there are messaging interfaces, key value, HTTP, blob store if you want to store unstructured data, and runtime configuration if you want to configure how your WebAssembly should run, and give access to dynamically configure your runtime configuration. And that Cloud Core interface was initially developed under Spider Lightning project, developed by Days Labs. Some people from Microsoft were working on it, and initially it was working with WebAssembly modules, defining interfaces at a low level, importing and exporting C functions. However, after WebAssembly component model and WebAssembly interface type was standardized, it was transitioned to use that, and then later on, this runtime, which was implementing the interfaces, was compiled into the Cloud Core interfaces set, which is being also standardized under WebAssembly system interface. And currently this runtime is not much in use. However, it paved the way towards kind of experimenting with the interface and allowing your Wasm components to run in the cloud and interface with cloud services. It's also important to mention that WebAssembly standard itself being developed further, and one notable thing that would come later on after it is standardized is a threads proposal. It has some experimental support in some runtimes. However, one most important thing being developed there is a shared memory, which would allow your Wasm components to share some memory and execute in parallel with some primitives to define your mutex locks and other primitives for developing parallel software. So now we have those interfaces. We can define our custom interfaces. There are WebAssembly system interfaces. However, how do we carry the support for extensibility and interoperability while still enabling cloud native integration? That's a challenge that two frameworks started addressing that challenge, namely Spin and Wasm Cloud. Spin is developed by Fermion and Wasm Cloud by Cosmonic. Wasm Cloud is a CNCF project, and Spin took an approach of integrating natively with Kubernetes. So their basic setup, from what I've researched, is to extend the Wasm runtime with your custom interface. So they've included some WebAssembly interfaces that are not compiled into the WebAssembly system interface standard, extended that with it their runtime, Spin runtime. Then they created a containerd shim for it, and then you would need to add support for the shim in your container environment, and then add the operator for your custom resources if you are defining how your Wasm workload is orchestrated in some custom way. So there are two parts to this. On the left, you can see the basically Kubernetes operator for your custom resource definitions. But on the it would be custom for probably everyone. However, there is some opportunity to standardize it, or maybe even skip it and run your Wasm workloads as basically containers. However, on the right side, you have the runtime class manager, which is also being developed by Spin framework developers, and it's a special case operator which is based on the proposal for containerd shim lifecycle support. So this is an interesting case because writing an operator to control the lifecycle of your containerd shim is, I think, haven't been really done. However, when you have your custom runtimes for WebAssembly supporting your custom interfaces, you run into a problem that you have a lot of runtimes, zoo of runtimes, supporting different sort of interfaces. And to control what kind of runtime you would like to choose for your WebAssembly workload, you need this sort of operator. So this is based on native WebAssembly tooling. However, one alternative is to continue relying on the WebAssembly standards, and that's the approach that Wasm Cloud took. And they rely on interface-based development, namely remotely linking WebAssembly interface types. So instead of having this setup where you have your host runtime embedded, certain interfaces can be swapped over to be communicated over RPC calls, And with WRPC, you can have your capability providers defined anywhere, for example, as a plugin on your runtime or on a completely different device in the network. And Wasm Cloud ships with a lattice, their network mesh through which different WebAssembly components and capability providers communicate and enable this sort of dynamic linking. And the most amazing part now, I think, is ability to dynamically serve WRPC endpoints. So you can, of course, statically link your interface with your runtime or with the WRPC. However, you can do runtime WebAssembly component interface introspection to see what kind of interfaces are being exported, what kind of functions are being exported. So here in this pseudocode that I took from the Wasm Cloud-based implementation, they are looking into the WebAssembly component, trying to see if it is exporting some supported interface, then directly serving that, or otherwise they are just directly exposing the functions over WRPC for other services to communicate with. And as long as you know the name, you can identify what kind of interface is being served, you can link different WebAssembly components from different machines through WRPC. And WRPC is transport agnostic, so you can implement your transport layer for WRPC over any communication protocols, maybe even locally. And what this enables is you can create your custom interfaces, dynamically serve them over remote procedure calls, and then distribute your WebAssembly components across network mesh anywhere. And WebAssembly bytecode and WebAssembly interfaces can be distributed using OCI registries. There was an attempt to build a WebAssembly native registry. However, there wasn't too much need in it, and they didn't find much use case for creating your own registry standard. So currently it works well with OCI, and you can distribute your WebAssembly interface types and WebAssembly bytecode directly through OCI. So compared to big Docker containers that are based on, for example, Linux emulation, you would include lots of libraries to emulate Linux behavior, but with WebAssembly, you are just exporting the core logic, and everything else is abstracted under those WebAssembly interface types. So the resulting artifacts become way smaller in 10 megabytes maximum size, mostly even kilobytes. So now I would like to demo quickly the local setup. And for that I need to change quickly to the mirror. So here for the Teltonika device, which is based on ARM Cortex A7, I've compiled the Wasm time runtime for WebAssembly, and that runtime can do on-device WebAssembly compilation to native code, and then execute it with sandboxing for the linear memory. And the implementation of it for this demo is quite short, like in 300 lines of code in Rust, and it is designed to run a WebAssembly component to communicate with MQTT. And I've already compiled everything, and I can demonstrate it here. So this is a simple echo demonstration. So I send a message, it should echo it back. If I send it, it responds to the this topic. And if we go to the WebAssembly component, which I compiled over here, so you can see that it's getting the message, constructing a new message out of it, and then passing it back, sending it to the topic called WebAssembly MQTT handler. However, I also configured the runtime to add some sort of permission control, access control. And if I go and say execute a Wasm component which publishes to MQTT topic for which it doesn't have permission, in this case, let's see if it's the correct one. In this case, it is publishing to the topic test. However, in my runtime, I implemented that the WebAssembly component can only publish to the topic starting with Wasm components to add some sort of like small isolation. If I do that, publish it here, the host receives the MQTT message, passes it to WebAssembly, and then WebAssembly tries to publish it on the test topic. However, host checks it and gives permission denied error. And another demo, I will skip this one. You can also configure the permission if you want to connect to some MQTT client itself with passing in a connection string. And one interesting demo is JSON parsing. So this is a bit more complicated one, where we are parsing the JSON object and then extracting a value out of it and passing it back just like echo. And with this one, you can see that it is extracting the hello message and putting it, echoing it back as plain text. And if we are supplying some non-JSON value, it would also like tell about some error, for example. And all of this is running on this little device with MQTT broker embedded in it. And if I look at the resource consumption, here it used, for example, 36 megabytes. And for this device, you only get, for example, 15 megabytes of free space in the user space. So you can even run more workload on this. So it is handling this situation well. And this is mostly it. So if you have questions quickly in a minute, but we can continue more later, yeah.
Please repeat the question in the mic.
What would be the best way to get started with Wasm?
If you want to get started, I suggest looking into the tools provided by Bytecode Alliance. They are maintainers of the Wasm time runtime, and they implement most of the WebAssembly system interface proposals in early stages. And you can experiment with the latest tooling and standards with projects around Bytecode Alliance, which is focused mainly currently on Wasm.
Thank you.
Yes, thank you. Let's have more chat after the break. I'm excited to talk about this even more.
Okay, thank you to Yerzhan and all of you. There is some